Hello and welcome to today's lecture on biostatistics. So we will start with a brief recap of the R language and then solve few examples in RStudio. Okay. So just to revisit our discussion of what is R, it's a software environment for statistical computing and data analysis. So it's an open source package, it is freely available, it has command line interface. But since for many users using a command line interface may not be beneficial or easy to handle, there are open source softwares which provide a graphical user interface so that it is widely used. And the best part of R is can produce publication quality graphs with mathematical symbols. So it's an interpreted language. This is just a print screen of the R console. You see, it is just you can just enter things here, but and you have and R has been widely used by statisticians. It was actually developed at the University of Auckland and it is now widely used. It has a support base where people contribute to its further development, and it has met the performance benchmarks comparable to that of GNU Octave or MATLAB. So it is reason why it is used for statistical analysis of big data as well as in business analytics. So you can download R from this rproject.org, rproject.org, and you can, depending on the software interface, whether Windows, Unix or Mac OS, you can download the appropriate file and install it. And so because it is a command line interface, so people have developed softwares based on R which have a GUI interface, and RStudio is one such of them. And in R, this is just a print screen of how RStudio looks. This is the command window where we type in numbers or whatever we need to do. This is the workspace which stores all the data that we generate, and here you are provided additional information on how to use it or what something means. Okay. So this is just an example of how I can create a vector in R, and so let us directly go to RStudio and see, rerun all these examples so that your idea is rechristened. Okay. So this was an example I had done earlier, but let me just see. So in order to generate a vector, so you can do all basic computation. I can write AA equal to 1, BB equal to 2. I can write AA power BB, so I can get these answers, BB power BB, okay, exponential of BB, so on and so forth. So and what you see is, if I drag this down, all these numbers that we are putting in are getting stored here. Okay, in terms of value, it has stored the value of AA, stored the value of BB, BC, whatever. Okay, so you can do the basic arithmetic. You can have, so sine of 30, as I pointed out yesterday, you have to write by pi by 180. So in order to convert it into radians, and only then will you get the value. Okay, so this is how you get 0.5. If you do sine of 30, you will get some other value. So remember that we have to convert every degree into a radian in order to use the sine, cos, tan functions. You can do a sine or sine inverse. Let's say we can do a sine of half, and you get the value of 0.523, which is nothing but this particular value. Okay, so arc sine, arc cos. You can do log 10 of 10 is 1. Okay, you can also do log of 10 comma 10, which is also going to give you the value. So you can put log 10 base 2. Okay, you can do just log of 3, let's say it is the natural log, and you will get slightly value because E is 2.7 something. Okay, so these are all the basic calculations in order to generate a vector, let's say. So I can write CC is equal to C 1 comma 2 comma 3 comma, okay. So C, and so as you see the format, the syntax is you get the variable name which is a vector, and C is for concatenate, and you give them item 1, item 2 separated by commas. Okay. So if I type CC and put an enter, it will give you the exact value. So this is how you create vectors. You can do elementary vector operations, like let's say you can do, so let's say CC is this, let's say you define BB as C of you can do CC and BB as another vector. I can do CC plus BB and I get the answer. I can do CC star BB. So you see that these are element wise operations. So that is why when I am doing CC star BB, 1 is multiplied by 4, so on and so forth. Okay. So if I want to multiply something throughout, then I should do, let us say, 4 star CC, then all the individual entries are multiplied by this factor. So for a scalar multiplication, you put a prefactor outside the vector, and for these are all vector additions, vector multiplications. What you see is these operate at the single element level. Okay. So if I go back to this PowerPoint, so this you can even create a same number repeated whatever number of times. So the syntax is very understandable. You write repeat whatever is the number is 1 or A or B, and times how many times you want to repeat, and you see you create a vector of the same number which is 10 times. You can repeat a sequence. So let us say you have 1 2 3, and so 1 colon 3 means would be 1 2 3, and this has to be repeated 5 times, and you can accordingly get this particular vector. You can also create a sequence. So this is another example of a sequence where you go from 1 to 7 in steps of 1, and you will get this particular thing. You can create a repeat of a sequence. So every time you put a bracket and you put an operator, it operates on this whole thing, and that is how you have a repetition of a sequence which is number of 5 times. So you have 7 7 7 7, so on and so forth. Okay. So this is just what I did, which was element wise operations on a vector. You can do all the calculations here. Let us go back to RStudio. Okay. If I go back to RStudio, now let us say I have my vectors, and what I want to add a vector online, okay, as opposed to typing them inside like this. If the vector is long, then it is difficult to enter. So what I can do is I can add the vector online. So in that case I can write dat is equal to scan till open brackets. So if I do enter, then it puts the command prompt here, which means I can enter anything. I put spaces, if I put enter, it again gives me the option of adding many more numbers. So you see the number 13 is written here because I have already made 12 entries. So this is the 13th entry. So it begins with 1, which is this entry. Okay. So I can keep on putting random numbers, and every time I put enter, it gives me the option of putting in any entries. But if I press one more entry, then essentially it will understand that is the end of it, and it has created this particular vector which has 17 items on it. So I can now type that and see what is the value of and you see that this is the way it is. So you see that depending on how you write it and how what is your font size. So when it is coming, you can only reach till 13th entry here. That's why from the 14th entry it is coming here. Okay. So in order to know the length of the vector, I can use this length of that. Okay. It tells me that there are 17 column entries in this particular vector. I can also, so the jargon for entering a character entry is slightly different. So let us say I can do this xstat dat is equal to scan. Okay. If I do this, if I want to enter characters, then what I have to do is, let us say Monday, Tuesday, Wednesday. Okay. So I put 2 times that. So in this case I have to, okay, let us see. Okay, I think I have to write dat is equal to scan what equal to char. Okay. So now, so by default this function scan always expects to get real numbers. So that is why you could see expected a real got m, which is a character. So if I put this statement inside that scan and what it is expecting is a character, then there is no problem. So if I now write that here, you will see Monday, Tuesday, Wednesday as the numbers being entered. Okay. I can add So, I can add, so let us say if I have x x equal to C of, okay, I can write I can add elements to x x by writing C of x x comma 6. Okay. If I write x x now, you see it has added. So, it is possible to add numbers into a particular vector, and as before, as I had shown you before, we can even put, so the order of the x x does not matter. I could have well written C of 6 7 8 comma x x, in that the vector range would have been changed. Okay. So, if I go back to the presentation, so the next thing, so of course, these are still numbers which I can enter and I can keep on entering on screen, but if you have a big file, then this function does not work. You have to use what is called, you can import data using various ways. Okay. So, this is an example where you can import data using CSV format. This is called comma separated variable. So, let us do this particular example. What I will do is I will create and I will open an Excel sheet, and let us okay. So, I have entered some numbers and I can save it in CSV format. So, when you do save as, by default it is always in Excel workbook, but what you can go down and you can choose comma separated values. Okay. This is CSV, and you can do the save, it prompts you this particular warning, but you can say continue, and this this is stored as a CSV file. Okay. Now, what I can do is I can do this, I can go to RStudio and I can write xx is equal to read.csv, and I can write file dot choose. What this means, so when you do this, it allows you to choose a particular file. Okay. So, if I do enter, it will prompts me this, and this is the latest workbook that we have had. This is a CSV file. I can open it and it gets chosen. Okay. You can select it. If I write xx here, and you see that these are the values which it chose. So, even though we did not explicitly enter the tags of what are the column names, in CSV these things are already chosen, and even the left row numbers, they were stored in the CSV format generated. Okay. So, if I go back to the CSV file, okay, so you can this is the easiest way of this is just another way of example of how you can choose these particular values. Okay. So, this is the most widely used system to import data, but particularly when you have big data. Okay. Now, let us get down to some examples of finding frequency, mean, median, so on and so forth. Okay. If I go back to RStudio, so let us say I will again enter another set of parameters. Let us say xx in the screen is equal to C of I have entered this random array. I can know the length of the vector by writing length of xx. Okay. It has 8 entries. I can find minimum of xx, which is 1, max of xx, which is 6. I can have mean of xx, which is 3.25. I can have median of xx, it gives me a value of 3. Okay. So, these are widely useful ways of doing of getting the statistics, descriptive statistics from your vector. Okay. And one more thing I wanted to show is, if you do table of xx, then you will get the distribution. So, how many values have value of 1? You have only one entry of 1. You have, it says that there are 2 entries of 2. Let us see. So, these are the numbers I have entered. There are 2 2's, and that is why when I do the frequency count, there are 2 2's here. Similarly, 2 3's, 1 1 1. Okay. So, this is a very useful way of getting the the statistics from these particular examples. I have shown you how to calculate the mean, median, minimum and maximum. You can also do the variance and standard deviation. So you can use this particular function of var to find out the variance of this distribution, SD to find the standard deviation of this particular vector. So in this particular example where you have how many entries, 1 2 3 4 5 6 7 8 9 11 entries, your variance is coming out to be a value of 32 and standard deviation is around 5.6. Okay. So you can also find out the standard deviation and square it to find out the value of variance, which will give you the same information, or you can calculate the square root of the variance to find out the standard deviation. Okay. Some more examples. So you can I'll show you how you can use this particular functions. Okay. Again, let us go back to our studio. Okay. So let's say I want to sort xx. So let us write a longer value, longer vector. Okay. So yy has 14 entries, length should give me a value of 14. So let us, so I already know the information, I can use these earlier values to find out this, but what I can also do is I can do sort of yy. Okay. And then you see that it is being sorted in ascending order. If you wanted to sort the same vector in reducing order, the other way around, so you can write sort yy comma decreasing equal to true. So in this case you have the reverse order from the topmost number to the lowest number. Okay. You can also have, let us say you want to some statistics, there are how many numbers in this vector which are greater than 2, for example. So I can write xx so there is 3 6 3 4 5 are the 5 numbers which are greater than xx. Okay. I can also write so I can ask at which position is xx equal to 5, it is returning me a value of 8. Let us see where I have the first value of 5, 1 2 3 4 5 6 7 no 1 2 3 4 5. So xx is equal to 5, it is returning me a value of 8. Okay. I can do another thing which is the summary of yy. So what it gives me are all the minimum, the first quartile, the median, the third quartile and the maximum. Okay. So instead of summary you can also use this function called quantile, and this is the same thing but given in terms of exact percentage. Again you see the minimum is 1, your first quantile is 2 as is showing up here, your median which is the 50th percentile has a value of 4, so your 75th percentile is this and the maximum is 7. Okay. So clearly, so in this case you have median and mean both reported. When you write quantile you will only get the plot of these actual percentiles. Okay. So these are the things that I wanted to these functions I wanted to show, these are useful. Okay. Let us take another example. So imagine you are doing a measurement where you are tracking or your aim is to correlate the cell. So a cell which is moving and you want to see whether when it is moving it is elongated or is it round. Okay. And what you do is you do this particular this is the data where you have two metrics for characterizing the cell phenotype. One is whether it is circular or spindle. So a circular cell would look something like this. This is your circular cell and this is your more spindle shaped. So this is spindle and this is circular. Okay. And you are, so these are of course, so you have a nucleus at the center. Okay. And you want to see what are the trajectories of these cells in 2D plane and you want to find out, so based on the distance it is moving, each of these have two population. Okay. Migratory and non-migratory. Okay. Same here, you have M and non-migratory. Okay. So this is just an example. So, in this particular example what we have is the distribution for let us say 22 such cells. For each cell you have the shape which is either a circular or spindle, and the phenotype which you characterize as non migratory or migratory. So, essentially both these metrics are categorical data, and you want to find out. Okay. So, from this table you want to find out what is the distribution of this data. So, I can first generate the table of the cell type. Okay. So, this is just the way to import the data into the R framework. You can do this command of table to get what are the different distributions. What you see is there are circular in shape, 2 of the such cells are migratory, and there are 9 which are non migratory, and in case of spindle shapes 8 of them are migratory, 2 of them are non migratory. So, this data kind of conveys the point that a greater proportions of cells which migrate are spindle in shape, and a greater proportion of cells which are non migratory are circular in shape. Okay. So, this is a way of plotting this data. You can do bar plot of this table and you have this particular distribution. So, let us go back to R. So, let us use the same data which is YY. I can write let us say bar plot of YY, and okay, figure margins are too large. So, this is perhaps not coming here, I do not understand, but you can also do histogram of YY. This problem is coming, we will see, but if you use these particular functions box plot, bar plot, let us reduce the file size a little. Okay. Now, you see. Okay. So, it was coming like this because this required a certain amount of space. You see histogram of YY will give you this particular distribution. It conveys the message you have a peak here and another peak here and then one corner data here. Okay. Let us see again if I could plot the bar plot here. So, this is your same plot plotted in bar plot manner. We can also do the same thing for box plot. Okay. So, this is the box plot, okay, with bars. What we can also do is we can, so if I go back to the presentation now, so this is what we had plotted, which is the bar plot of the table, and you see that in case of these cells which are circular, you have a greater portion which are non migratory, okay, which are circular in shape, and lesser portion which are migratory but circular in shape. Okay. So, I can also represent this data by plotting this side by side. So, this would be how it would look like. So, if I write this particular framework which is beside equal to true, then I would generate this particular plot. Okay. So, in terms of migratory, and these are circular which is very few, and and spindle shape which are very high. Okay. So, I can use a similar thing to generate the plotting for R. Let us say you have a trajectory of a cell which is moving in xy plane, I can, and you have imported the data. Okay. So, you can clearly see that by plotting the data as, so you have read this particular data and the data has become, data is as represented as x and y, and so what you see here is you have first imported the data, and in that case you are plotting data colon comma 2, data colon comma 3. Why are you choosing the second and the third column? The reason is because when you import your, you have a row or a column which gets inserted, which is the row number. So, let us go back to R. So, which is the vector that we had, let us again have ZZ is equal to read.csv file.choose. Okay. So, if I again read my workbook 3 and I plot ZZ, so you see that there are 3 columns which are generated. This one was the default entry in Excel which we do have no control over. So, this is why you have to neglect this particular column and you plot x2 and x4, and this is what we have done in this PowerPoint file. This is what we have done in this PowerPoint file, whereby we have plotted data colon comma 2 colon comma 3. This is high, and then this is the corresponding the plot in xy plane. I can also, what I can do is I can give a title to this particular plot, which is migration trajectory, which appears here. I can set my limits. So, x lab, so I can set my labels. So, x lab is x coordinate, y lab is y coordinate, you can enter here. You can, what you can also do is you can change with the play with the color of this particular trajectory. What you see here is cull equal to red, means essentially we are resetting this trajectory color to red. And the last is you can also put x lim. X lim is for limit. So, if you want to probe it within the certain domain, you want to plot it within a certain range, you can have control over x range and y range. With that, I think you have gotten a good enough handle of how to do this. Okay. So, we would stop here. I would just go back to let me go back to this particular slide. Let me just go back to RStudio once more. So, you can have these particular plots. Let us, so we had plotted histogram of yy, you can plot it in histogram version. Okay. So, if you write histogram of yy comma frequency equal to false, what it does, it actually converts this data as density or relative frequency, and you, instead of absolute values, you will get a range. Okay. So, here itself, for example, in terms of yy, I can write other values, I can change the color of this, and so on and so forth. With that, I hope you have been convinced of the power of this R software, which is open source. You can freely download it, install it, and use it for your own purposes. Particularly when you are handling, you should get into the habit of calculating standard deviation, mean, and all these descriptive statistics, even of generating these plots in R. Okay. With that, I thank you for your attention, and we will meet again in next class.